Okay, we are live. We are live.
All right, we're getting ready to start the last session of the day and of the conference. And I'm Mike Foer, but I'm introducing Dr. Jill Steinbach-Atkins as our other moderator. And so we have 4 talks in this session. Go ahead and get started.
Thank you. Thank you. So today I'm going to be talking about a comparison of emulsion-based and electrosprayed particle architectures to sustain the release of small hydrophilic agents. So the focus of our laboratory is to create new delivery vehicles that enhance the delivery of things like drugs, genes, proteins, and peptides against different pathologies, with our primary foci being viral, sexually transmitted infections, bacterial biofilms, and cancer applications. And we do this in the form of 2 different platforms of electrospun fibers and polymeric nanoparticles. So for some of you who may not be familiar, given the IEEE nature of this conference, some of the advantages of using polymeric nanomaterials are that they can provide localized delivery, provide high encapsulation of agents to increase local concentration. They enhance agent stability, particularly in the environments we're interested in, of the vaginal or oral microenvironments. They provide tunable systems with sustained release properties. You can often use material choices that are non-inflammatory, FDA-approved, biocompatible polymer materials. And you have the ability to surface modify these carriers with desired characteristics to enhance their transport through tissue. And really one of the things I want to talk about in this presentation is that they provide the ability to provide long-term sustainable delivery anywhere from about 1 week to 1 month is highly desirable for a number of different medical applications. So although we work in the viral and bacterial realms, I'm going to be framing this work in the context of nanoparticle transport in cervical cancer. And one of the particle platforms we use for delivery for cervical cancer and other applications is called polylactic coglycolic acid, or PLGA. We have the ability to encapsulate a variety of agents like siRNA, drug, DNA, protein, and to co-encapsulate those agents within a particle. We have the ability to protect these particles during transport to provide stealth-like properties, antibodies for targeting, and also facilitators to enable better cell internalization. So one of the things that we're concerned about when delivering particles, particularly to the female reproductive tract and other areas of the body, is how can we make these particles such that they can overcome the inherent obstacles present in the areas we're delivering. And so here's a nice example of some of the challenges when we look at mucus. So mucus inhibits a lot of bacterial and virus penetration into tissue, into underlying tissue, where you can often have infections here. And in addition, people often design these particles to circumvent mucus, to move through mucus before the mucus is cleared, hence also clearing the nanoparticles. It occurred to me in the context of some of our work with cancer that the tumor microenvironment poses some of those same challenges for nanoparticle delivery. And so here you might have different interstitial fluid pressures for tumors, or the matrices of extracellular matrix surrounding cells in which particles and other chemotherapeutics have to navigate to actually get to the source of cells within the tumor spheroid or tumor tissue environment. So people design nanoparticles in sort of 2 different ways to overcome these obstacles. One, either making them mucoadhesive or muco-inert with things like PEG on the surface. They can change the density of PEG to enable better penetration through the tissue. One of the things we had looked at in one of our early studies, particularly for viral applications in the context of HeLa cells, is we had looked at how can we increase our gene delivery to cells. So as you may know, gene delivery requires, relative to drugs, that the cells actually internalize genes or oligonucleotides, and so we were looking at how can we modify our particles to have some of these stealth-like properties to navigate tissue while also being able to enhance cell internalization. So here we encapsulated a fluorescent dye, C6 within the particles, and we modified this with facilitators of cell internalization that are a variety of ligands, including we had unmodified particles or particles surface modified with things like chitosan that's really sticky, or the cell-penetrating peptides, penetratin, EB1, MPG, or MPG, del NLS, that allow actually cytosolic localization of the cargo that we're delivering. And so here's just an example of some 2D experiments we published a while back in which we would show controls of, well, first of all, the cells are stained with Hooks for the nucleus, red for the Texas red, with Texas red for the cytoskeleton, and the green represents our C6 nanoparticles. We have untreated cells and cells with unmodified nanoparticles. On the left is controls. And here I show you what happens when we modify the surfaces of these particles with different cell-penetrating peptides at low and high densities respectively. And you can see from the green how much total cell association and also internalization is improved. We took one of these, we ran flow cytometry data I'm not showing here, and we identified that the MPG-coated particles provided the most increase in cell internalization. So we also verified this with different modifications on the nanoparticle surface, and saw as we increase the amount of MPG on the nanoparticle surface, we can obtain much greater amounts of nanoparticles, here shown in turquoise, within the cells. In fact, we could increase cell internalization by about 70-fold. But one interesting thing, so then there was I began that work a while back, and when I started here, I started working with Dr. Herman Fribos, looking at how can we use these particles to localize delivery for cervical cancer treatment. And we had looked at these particles, you know, for female reproductive delivery and in 2D assays to see how could we increase gene delivery using these modifications. But we hadn't looked at them in the environments, the tumor microenvironments that we can grow mimics to represent within the lab. So briefly, we formulate our nanoparticles with an emulsion-based process, and then we wanted to look at how different modifications of these particles could penetrate tumor matrices, either using a liquid overlay spheroid, where this spheroid formation method generates rather large tumor spheroids, or the hanging drop method, where you can form very, very small and more tightly clustered tumor spheroids to represent that cervical tumor environment. And so using this particle platform as a basis with cell-penetrating peptides, we also looked at stealth modifications or co-modifications or co-treatments of different particle groups comprised of unmodified particles, particles coated with MPG, VIM, which was a tumor targeting marker, or PEG for stealth properties, and also formulated some particles that had hybrid modifications on the surface. And we wanted to look at how well were they not only taken up in 2D culture, because it's well known that while PEG, for instance, can provide stealth properties, they're also not internalized extremely well, and hence that's where we saw the cell-penetrating addition would provide more favorable internalization properties. So we looked at these in 2D assays, and we saw increased uptake using MPG or hybrid MPG stealth particles after 24 hours. And then moreover on the right, we tested some of these, so MPGs in panel H relative to unmod particles in the actual tumor spheroid in G, and we could see increased localization and association with the tissue after this modification. What we really wanted to look at is how far could we get as a function of modification, how far could we actually get these particles into the tumor spheroid matrix. And so here we show fluorescent intensity on the y-axis with your distance from the spheroid periphery in microns on the x-axis. So this essentially denotes how far these particles are traversing through these spheroids. And we saw an interesting thing is that if we had MPG modified particles, they did very well in internalizing with cells within about the first 100, 125 microns of the spheroid matrix, whereas the PEG, as expected, would penetrate more deeply. In comparison, you can see from the brown line, so the brown line here, well, the brown line, that MPG co-modified particles did not perform nearly as well as you expected, so we sort of changed our rationale and decided to co-administer these two different particle types, either PEG modified alone or MPG modified alone, to see how they might affect transport in an increased variety of tumor types. So I'm not going to go through this in depth, but to broadly show you what we did, we created two different kinds of tumor spheroids. Again, we have these liquid overlay, larger tumor spheroids on the top. We have hanging drop spheroids on the bottom. They're more tightly clustered tumor spheroids. We looked at tumor cross-sections on the left and composite images on the right as a function of three different cervical types of cells, so HeLa cells, Kaski tumor cells, and SIHA cells. And we delivered either no treatment to these cells, unmodified particles, MPG modified particles, PEG, or MPG co-treatment particles. And so we took this data, only a subset of which I'll show today, and particularly in the hanging drop method, that allowed us, because they're smaller tumors, to enable greater amounts of particle penetration relative to liquid overlay. And one trend that we found in general is that modification period on the particles, whether it's MPG, PEG, or the two particle groups delivered together, all provided increased uptake and penetration into these tumor spheroid areas. We also noted that while HeLa and CHAs provided moderate uptake and penetration, caskies, which are very tight tumor cells, provided very little room for the particles to get into the tumor matrix in comparison to the HeLa and CHA hanging drop spheroids. So we've also, again, looked at encapsulating different drugs and active agents and how these particles perform in terms of efficacy on these 3 different lines, and they are very efficacious. We looked at this in 2D, actually with doxorubicin as our encapsulant. We looked at this in 3D. And one thing from all of this that we saw across the board was that when you make particles with these small hydrophilic encapsulated agents for delivery to tumor cells, while we can achieve from a particle loading basis, the MPG, PEG, and co-treatment particles across all cell lines were more efficacious than unmodified, this is also very tightly governed by how much you can load into the particle and how much is released over time. So I wanted to provide this backdrop so we can understand why we need to develop particles that have better release and reproducible loading characteristics. So in summary for this first part, we just have the surface-modified nanoparticles, as expected, enhanced binding and penetration, and in fact, we think that the co-treatment will enable better localization depending on if you're within a close proximity to the tumor periphery or more toward the center of the tumor. And this may be used different tumor types, and spheroid forming methods may lend info for different clinically classified tumors, is our hope. HD spheroid showed an increased uptake across all cell lines, and while I didn't show the data that's relative to the larger liquid overlay spheroids, overall the MPG, PEG, and co-treatment models provided higher uptake. In the same thing in liquid overlay spheroids. While they had overall lower uptake, the trends were pretty much the same. And so our hope is that surface-modified nanoparticles may impact more complex or variable tumors, which would be really important in clinical applications if they had the ability to either genotype or phenotype some of the patient tumors and understand their cell origin. And one thing, the focus we want to look at is how can we unify loading and release from the formulation processes. And so briefly, in what pertains to some of the materials submitted for this presentation is how can we design nanoparticles to meet these sustained delivery needs. It's pretty much well known that for a lot of polymeric particles, you get inherent burst release. It's something we can't get around. You can do different polymer blends. We know other groups have done that. But to show you kind of a worst case example for delivery of a small molecule, small hydrophilic chemotherapeutic, here's a plot we have. We were delivering melphalan for ocular cancers. And you can see that regardless of formulation, really within the first few hours, all of the melphalan is coming out. And moreover, due to our fabrication process, the emulsion-based process, we're losing a lot just while we fabricate the particles. So we started thinking, based on other literature, how can we improve our sustained release characteristics over time and make it come closer to zero-order-based release mechanisms. And so in some of our other work in the lab, we're formulating electrospun fibers for some other applications, and it occurred to me that we might be able to utilize some previously published work on electrosprayed particles to provide better sustained release. And so for sustained release, there's this idea that the combination of liposomes and polymeric nanoparticles, they've been widely used. Both platforms have demonstrated biocompatibility. They can deliver encapsulated agents to target sites, improve efficacy, and also minimize adverse effects often seen with systemic treatment. So they might be good for localized delivery. However, active agents often undergo, as I showed in those plots, more rapid burst release, and in particular for lipids, it's often even worse. So the thought is that polymer-lipid combinations may offer opportunities to more subtly tune active agent release. And we can fabricate polymeric nanoparticles with a variety of techniques, but the ones that we have going in our lab are emulsion-based and electrohydrodynamic atomization, which is also called electrospraying. And so we're hoping that these synthesis strategies can produce some complex architectures of which we're looking at, or began to look at in this work. And so thanks to my student Keegan, who actually worked on this the past summer and he transformed our electrospun fiber spraying system into one that's more compatible for the spraying of particles. So here we have different formulations that we have done in the past, emulsion-based, where you can create a polymer matrix core that has drug as denoted in red through it. And we can also do an in-situ and have done an in-situ lipid coating process or do a post-process lipid coat on these particles to modulate release. And you can also look at electrosprayed formulations. And here, looking again, you can spray core particles, you can spray conventional core shell particle. And you can look at what happens if you put lipid coats on these to make these hybrid lipid polymer particles. And so I'm just going to show you some preliminary release work from his summer in the lab, comparing our core and our in situ lipid coated with the core electrosprayed in two different types of electrosprayed particles, what I call conventional and perfusion. And the difference is that in the conventional, we had the PLGA matrix on the shell, PLG matrix with drug in the middle, whereas the perfusion only had drug in the middle and no polymer. And so we initially looked at this and we saw very favorable release from our uniaxial and coaxial groups relative to, again, the pretty poor release that we saw in emulsion-based characteristics. We did a more thorough characterization of this, and one of the drawbacks about using electrospraying is that particle sizes tend toward the more micron size. So where we're at now, and Keegan, he has unfortunately not had time to be in lab this semester, but we're trying to get these particles closer in size by adding a number of ionic agents to our emulsion-based particles that range from about 160 nanometers in general. We're trying to get these other sizes down because of their favorable release characteristics. And then here I just wanted to show, beyond the nice release characteristics, which we've more thoroughly characterized here, we can see from panel A that electrosprayed formulations after loading load a higher amount of activation. It's really the synthesis process. You don't have room for these small hydrophilic agents to leak out during the processing. And then we have the emulsion base where you get lower loading. It gets even worse when you put a lipid coating on it. Here in panels B and C, I just want to show as a function either the amount of a small hydrophilic agent, rhodamine, mass per mass, or as a percent total loading, how we get much more favorable release characteristics here just over a period of 1 week for either our uniaxial or the two variations of coaxial. And we're looking at moving this forward. Currently we're trying different polymers, polymer blends, and solvents to actually get our sizes down to make them similarly sized to our emulsion-based fabrications. And we're hoping to continue our work to actually apply this, go back and apply this to oligonucleotide delivery, either in the context of cervical and ovarian cancers, where we can take advantage of the early part of this talk, where I showed you how we can modify it with different agents to facilitate cell internalization, but also modulate activation release in a better way to hopefully negate some of the burst release we're seeing. And then we would like to ideally use these in some of the new ovarian cancer models that we're developing in the lab. And so yeah, in summary, core shell architectures produced via electrospraying are capable of sustaining the release of hydrophilic agents. Polymer nanoparticles, you can modify these with a lipid coating, and while we've done this with our emulsion-based formulations, we still need to move this forward to do that with our electrosprayed formulations. Our data here suggests that polymeric core shell lipid-coated particles, or just polymeric core shell particles, have the potential to really do a great job in sustaining the release of rhodamine B. That's no easy feat. And in future work, we'd like to utilize this to either reduce administration frequency of hydrophilic activations or just extend the delivery through which we can deliver these hydrophilic agents alone. And we are continuing, while I show this in the context of our cancer work, ideally it would be great for a lot of our applications where we're delivering other hydrophilic agents, including slightly larger peptides, some proteins and all that also show very challenging release profiles. So of course, I couldn't do this without my collaborators here, so thanks to Dr. Freeboot sitting over here, who is a primary collaborator on the tumor spheroid aspects of this project, our funding opportunities, and I couldn't do this without the people that work so hard in my lab to do this work. And yeah, if there's any questions, I'm happy to answer them.
You've got coatings you put on the nanoparticles that help facilitate penetration. Do you have to characterize do you have to do separate characterization for any kind of drug that you put in? Does the payload of your nanoparticles affect penetration not the same way, but in any way that you have to worry about that?
Yeah, so I don't think the payload affects penetration as much as really what is on the surface affects that. But we have to do thorough characterization for every batch we do for whatever encapsulant. We need to know how much is loaded. What can change is for instance, oligonucleotides for siRNA, for instance, if there's a charge that can bind to our surface coating, so can decrease release characteristics, which is why for some of this, which with and without lipid, we really need to look at how these, are we slowing release down of our active agents due to a lipid? Like how does that modulate release? And beyond the lipid that's on the coating, if you have that conjugated to your peptide of interest, could things get stuck and then not get actually released
So
as
it's
they're
not as
supposed
much
to?
about penetration, it's about release once it gets there.
So I think it's really both. It's both. So you need the coatings to help penetrate and to help internalize, but then with that particular coating and determined by the density, you know, the chain lengths of those coatings, can you get your active agent out? Yes, it's an optimization problem for sure.
What is your target penetration length that you would ideally like to see?
Yeah.
You know, because you said PEG, you know, was 200
Yeah.
microns. Is that what your goal is, to be able to penetrate as good as PEG, or do you want it to penetrate deeper? What is needed?
Yeah. So PEG. Yeah, PEG is the ideal for now. I think it depends on tumor size overall, right? So these are just spheroids, and actually that 200, 250 microns is about half of the size of our tumor spheroid. And in these studies, the time ranged from like an hour and a half to 24 hours where we saw that penetration. But ideally, you know, if you have a tumor over like clinically, right, over a centimeter, yeah, I mean, it would be great. You could consider giving a longer period of time to see how well these would penetrate, right? They probably need, what I'm saying is you'd probably need longer than the 24 hours here to penetrate larger tumors, but it gives some indication how far you can get them in. And I think another thing that people, I think another exciting thing here is looking, at first I was a little bit hesitant with the cell-penetrating peptides because we know they're very charged and get hung up on things, as shown here, but it's very nice because once you see the PEG particles go through, you have an absence of particles, unless you're delivering a particle that can actually get stuck in that first time frame too. So, and not to mention the more migratory cells at the rim, that could be a real positive of combining co-treatment strategies. But no doubt, I think the real tumors we're going to be looking at are larger in general, and we're going to have to figure out a way to address that.
Totally unrelated, but what is the strength of your Electrospray PLGA particle?
Strength?
The strength, yeah, tensile strength
Of the particle?
Of the fibers, I'm sorry, the fibers.
Oh, so
Do you know? I'm just curious.
I do know. So for another study, we looked at PLGA and PCL, tensile strengths, and I will say, I don't remember the values, but they aligned quite well. I can't remember. It was like 100 to 200. I hesitate to say, but I know it was like, you know, numbers were like 100 to 200, and I'd have to look into that. But it aligned well with, no pun intended about the aligning, but aligned well with what literature had said for those fibers, which we have not. So probably stronger than collagen, because these are, in the fibers, which I did not discuss as much here, are more, they're paper-like or almost like a plastic bag, you know, so there can be some flex depending on what you're putting in them. Yeah.
Thank you.
Thank you, guys.
الديسكشن موجود على اللابتوب فخلاص.